In this video, we'll describe in a bit more detail how we can use sparse coding to extract some features for a given problem. So one of the most popular usage of sparse coding is to extract features. That is, say we want to perform a particular classification problem, and we would like to use our data and find a representation, a new representation for our data, which is going to make the problem of classification easier. So specifically, imagine I have some label training set where I have some inputs, and each input is associated with the class label. So imagine, say, that the inputs are a set of images, and YT is the class of the image. Well, to extract some feature, what we could do is we could first train a sparse coding dictionary on the data set that only consists of the inputs. So we've thrown away for now temporarily the labels YT. So if we run our sparse coding or dictionary learning algorithm on that data set, this will give us a dictionary matrix D. And from that dictionary matrix, well, I could then take all of my inputs and compute what's the sparse latent representation based on this learned dictionary. And now what I could do is just take my original data set and change it in a way where I'll remove the original input and I'll replace it by this sparse representation. And so now for any classifier, I can just use my favorite classifier, whether it's a neural network or a support vector machine or a decision tree or any classifier. I can just train it on the new data set where I've replaced the input by its sparse coding representation. And from it, I now have to predict, again, the label. But now I have to predict it from the extracted features, from the sparse representation. And now if I had my system was confronted with a new input X, well, then the process of classifying it would correspond to first inferring its sparse coding representation H of X, and then I would feed it to my classifier that I've trained here. So while this part gives me a D matrix, this part gives me a classifier, say H F of my input, but now the input that I have to give it for my classifier F is actually a sparse coding representation, H of X, much like, and that's because it was trained on these types of features. Okay. Now, for this to be meaningful, to make sense, you essentially have to believe that the sparse coding representation is going to make the problem easier. That is, my data is such that there is a sparse representation which will identify features that are more directly related to what's the class label associated with my data. So one such type of data is image data. And in particular, let's consider image data that corresponds to handwritten digits. So I have a very small image, and in the image, I have a handwritten character. So this would be an image that would be labeled 2. So I have one, that would be one a pair of example with which I want to train my learning algorithm. Well, if I run sparse coding on a bunch of handwritten digits images, so I would just scrap temporarily while I'm running my sparse coding algorithm the label and just run on the images itself. Well, we have an illustration here of the types of features we would get. So now each little square here, so that's a square, that's another square, that's another square, and so on, is a visualization of one atom in my dictionary matrix, one column. So I can visualize it because each atom is a vector of size number of inputs. It's the same size as the input size. And because the input is an image, then I can just reshape my vector also into the shape of an image. And then in the visualization, if the pixel is gray, it means that the value of the vector for that pixel is 0. If it's white, then it's positive, and it's black, it's negative. So this essentially corresponds to the sort of illustrative visualization of what each sparse code element encodes. So if in my sparse coding representation, the code associated, say, with that feature had a large positive value. So if this was the first feature, so if h of x1 was, because this would be the first feature, if it had a large value, it would mean that if I was to reconstruct the original input, I would add 1 times this little image here. And say if this would be the other image, then I'd add also this part and so on. Okay, so that's why this is a meaningful visualization of the representation. And now we see that each sparse code actually has learned what looks like essentially a bunch of pen strokes. So this would be a pen stroke like this. This would be a pen stroke like that. And this one would be like this. So essentially, sparse-coding representation would be a big vector that identifies which are the different pen strokes that are present in some given image. And in fact, if we were to ask someone to describe the problem of classifying digits, entered digits, then it would probably actually use a description that's based on pen strokes. So to describe it too, I might say, well, it has a sort of a bar on top, it has a loop at the bottom, and so on. So we can see that intuitively this seems to make sense. This would be a nice way of representing digit that makes the class information much more obvious than just the raw value of the pixels. So this is why for image data, in this particular case, entered digits, sparse coding features work well in practice. In fact, we could actually train our sparse coding dictionary on a different type of data set. So if we had a large collection of unlabeled images that did not exactly correspond to the type of images we wanted to classify at test time, we could still use the unlabeled images to extract a better representation and see whether it transfers to my main important problem that I actually want to solve in terms of classification. So this is actually known as self-taught learning. So it's a combination of unsupervised learning and transfer learning for those that know more about machine learning. So these are unsupervised learning and transfer learning are two well-known types of learning, and self-taught learning can be seen as a combination of both. So in self-taught learning, the idea is that we want to train some features, but on a different input distribution because we might have more data from that input distribution than the distribution for which we actually want to solve a particular, say, a classification problem. So here's a concrete example. Imagine I had a lot of handwritten digits, a lot of images of handwritten digits, and that those were actually not labeled. I didn't know no humans went over the images and actually specified the label for each image. And now imagine that what I really want to do actually is classify handwritten English characters, so alphabetical characters, and not numerical characters. And but imagine I actually have very little training data for that. And now, can we still try to improve things by leveraging my unlabeled data, even though it's a different input distribution? So they're not; these are numeric characters, and these are alphabetical characters. So they're going to look quite different. And also, they might come from different people that actually drew them. So, so here's the experiment taken from this paper by Reina Battle, Lee, Packer, and Ng. They're the authors, the researchers that introduced the notion of self-taught learning. So in this experiment, they did exactly what I described. They took a lot of unlabeled digit characters, handwritten characters, and they trained, they either did nothing with it, so they didn't use it to extract a feature representation, or they trained a linear PCA representation from the digits data, or they trained a sparse coding representation, so they trained a dictionary matrix from which they could extract a sparse representation. And now they use these features to classify English handwritten characters, so alphabetical characters. And so what we have here is the performance for different training set sizes in the label data set. So we see that these data sets are actually fairly small in this case. So we can hope that we can leverage the information in the large unlabeled data. And so we have the performance if we use no feature representation. So we just use the XT raw representation, or the PCA representation, or the sparse coding representation as learned on the different data on the digits data. And what we see is that using some sparse coding, we often see an increase in the accuracy for 500 and 1,000 in this particular experiment. We saw better performance, better accuracy than if I had used the raw original representation or even just a PCA representation. And for 100 in this particular experiment, the performance was almost the same as if I'd used the raw representation, so we didn't lose much really here. So this is another illustration that sparse coding features can be useful for performing classification, as if we use that as, in a sense, a pre-processing step for our favorite classifier.